Good morning. Welcome to today's lecture. You are going to learn about a two-sample t-test for engineering experiments. It's a statistical test widely used in many science and engineering applications. In fact, mechanical engineering is one of the largest users of this testing procedure. So let's get started. The first thing is a Minitab. It's a software used to do all the statistical calculations. Of course, you can use the Excel spreadsheet to do the same thing. However, the most challenging aspect is the interpretation and significance of the test results. It's called as a sample test. Let me give an example. Let's say that a company is purchasing 10,000 ball bearings for an assembly from a manufacturer, and they are testing only 10 bearings to make sure that these bearings can meet the specifications given by the manufacturer. So we call as a sample, one sample with the 10 bearings, therefore the sample size is equal to n and n is equal to 10. It's called as a student test because we are taking a semester-long course and learning a lot of material. But your test and exams represent only a small portion of the material that you learned. Therefore, the student test is also like a sample test. Now, it is called as a hypothesis test. The hypothesis, what is hypothesis? If I do this, then this will happen. That's called hypothesis. So you have to make up a hypothesis and then apply the hypothesis to the test results to see whether we got meaningful results or not. This is the hardest part. This is the most confusing part for the students, and I will explain that as we go along. Then we have it's also called as a two-sample test because we are trying to compare two different samples or two different groups. For example, there are two different student groups, or you may have two different machines, two different processes, two different treatments. So you want to compare these two groups and then finding out which group is better or worse. So, for example, let me give an example here. Let's consider two machines A and B. Both machines produce shafts, and you are measuring the tolerances of the shafts and then trying to identify which machine is capable of giving better tolerances. Are these two machines give the same tolerances or different tolerances? Which one is better? So that's the main purpose of this test. So we call this as a two-sample test. And some applications are in various fields. In mechanical engineering, we use this procedure to compare the production rate of two different machines or the quality of two different manufacturing processes, or we are comparing the tensile strength of two different materials, or even if you take two vibrations of two mechanical systems. So you want to compare various things and then identify which system is better. So that's the main purpose of this application in mechanical engineering. In chemical engineering, people use this technique to determine the effect of catalyst on the yield of chemical reactions. In the area of medical field, they use this methodology to determine the effectiveness of new drugs. And similarly, in science area, for example, we are trying to determine the contamination levels of two lakes. Lakes have different nitrogen level contamination. So we try to determine that using this methodology. And even in the area of businesses, like if you compare pizza delivery time, there are two pizza companies. We want to compare the two pizza companies, which one delivers faster. So we can use this testing procedure to decide which business performs better. Okay, now we will turn into some statistics background because in order to fully understand a test, we need to have some knowledge of statistics. As you know, the normal distribution is a standard thing in the t-test. You can see a normal distribution of some parts. We call it as a population. To give an example, let's say that you have a bearing manufacturer who produces millions and millions and millions of bearings, and those bearing distributions are given by this. So the population refers to a very, very large size, all right? And the mean value of the population is given by the symbol mu, and the standard deviation is given by the symbol sigma, and the x is some kind of a dimension which you are trying to measure. So x is a variable. Now, if I take a sample from this population, the sample size is very small, like somewhere between 10 to 20 bearings. But the population refers to millions of bearings. So if I take 10 to 20 bearings, and then if I do one sample, if I do a test, finding out the mean value is called as X bar, and the standard deviation is called as S. And keep in mind the distribution is not quite normal distribution here. It is not a normal distribution. In order for the t-test to be valid, you have to have a normal distribution. So what they do is they run multiple samples. You take several samples and then plot X bar. That means the average of each of the sample. You make a distribution and you find out the standard deviation of this X bar. And it turns out it's difficult to do multiple samples in the industrial environment. So we want to do one sample, but still want to find out what is sigma X bar means. So for that, there's a statistics theorem called as a central limit theorem. If you have done statistics class, you probably come across a central limit theorem. The central limit theorem says sigma X bar is given as S over root n. So with one sample, we can determine sigma X bar as well as we can find out the mean value. When I say one sample, it means not one part. It means 10 parts or 20 parts. Somewhere between the sample size ranges from 10 to 30. And so, in summary, the population is represented by the mean value as mu and the standard deviation as sigma, and the sample is X bar, the mean value, and the standard deviation is sigma X bar, which can be computed using this equation. So now, what we are trying to do here in this test is we want to use a sample X bar to figure out what would be the value of mu. So our goal is, because we don't know the population mean value, so we're using this one to determine the new value. Okay, now we turn our attention to the equation for t-score. The t value is given by an expression, the sample's mean value minus the standard deviation divided by the standard deviation of the mean of all the samples. So that's where we represent the t value. That's for one sample. For two samples, we write an equation like this. For two samples, t is given as x1 bar, the sample 1, sample 2, and then we can write the equation in this form. And of course, you can determine the sigma x bar, subscript x bar as given by the standard deviation of the samples, and the number of parts in the sample can be used to calculate that. So that's where we determine the t value. Now, once in order to determine the t value for the two sample test, you need to know the mu1 and mu2, but we do not know the mu1 and mu2. That's what we want to find out. Are these two samples have the same mean values or different mean values? We do not know that, but we are trying to figure this out. So now we have to apply a hypothesis. So this is where the hypothesis comes in the picture, because we really don't know these. These values we know. We know x1, x2, and this value is known, this value is known, but we do not know these values. So we have to figure out that using a hypothesis and apply a hypothesis and then decide. So assuming that null hypothesis is valid, what is null hypothesis? Null hypothesis means h0, h sub 0, which is equal to mu1 minus mu2 equal to 0. And then the alternate hypothesis is called h1, which is the mu1 is not equal to mu2. So mu1 can be greater than mu2 or mu1 can be less than mu2. So we call this the alternate hypothesis. Now, in order to determine t value, that's first thing to do is we're assuming that null hypothesis is valid. If you assume null hypothesis is valid, then this term will become 0. And then calculate t value. Okay, so based on that. Okay, now we will give an example to illustrate the things we talked so far. Let's consider an example where we want to identify the effects of two catalysts on the yield of a chemical process. The catalyst 1 with about 8, the sample size is 8, and then the mean value of the sample is given this, and the S value is the standard deviation given as 2.39, and catalyst 2 has got a similar data here. So how do you solve a problem like this? Is the step 1 is we want to use an equation we presented before for the T for the two sample test. So you look at the T, calculate the t-value, assuming that null hypothesis is valid, which means mu1 minus mu2 equal to 0. So the rest of the information is given here. So we can calculate step 1, and it turns out is minus 0.354. Now we want to place this t-value on the H0 plot. Now how does a H0 plot will look like? A H0 plot would be something like a Gaussian like this. This is all the H0 plot for various t values. So the t is plotted here. So this is a 0. This will be, let's say, this minus 4, and this is plus 4. So this is a typical plot of H0 for all the t values. Various t values, you can make a plot like that. Now we want to place your t value on this one. So what we want to do is we take this is t equal to minus 0.354. So since this t value is well within this range of minus 4 to plus 4, we are going to draw a conclusion that both catalysts will give the same effects. Both have the same mean values. So in other words, do not reject null hypothesis. Null hypothesis is valid. Do not reject null hypothesis, and both catalysts will give you the same yield. Okay. But if this t value is outside this range, then it could be the one catalyst may give a different effect than the other catalyst. Okay. Now the final thought from the previous example shows that the yields are same between the two catalysts. But what is the confidence level at which this conclusion is drawn? That is probably the most important engineering question you have to answer. What is the significance of that test? Are you really confident that both catalysts would give you the same effects or not? The reason is, if you look at the plots of the null hypothesis and the alternate hypothesis, this is alternate hypothesis where mu2 is less than mu1. This is null hypothesis where mu1 equal to mu2. Here, H1 where mu2 is greater than mu1. You can see the t distributions shown here for null and alternate hypothesis. It turns out there is an overlapping region here. There's an overlapping region. So you are exactly here. So your value is somewhere here. So let's draw that. That is t is minus 0.354. Now, how confident are you that your null? We don't want to reject null hypothesis. So you can see that, of course, this defines that null hypothesis is valid. But if you are in the overlapping region, there is a risk involved. So for example, in this graph, this is a really fundamental plot. We need more time to explain this graph. If you understand this particular graph, you really understood the process. Because this is a graph that gives rise to the consumer's risk in purchasing something. There's always a consumer's risk in the process. And of course, there is also a manufacturer's risk in selling a product and the consumer's risk in buying a product. We call it alpha and alpha error for consumer's risk and beta error for manufacturer's risk. So those things are well understood. They're real engineering things. That's what we need to go and explain more about it. Okay, thank you very much.